Electricity is truly amazing, isn't it? It powers our homes, our schools, and even our toys. We use it every single day, often without even thinking about it. From the lights that brighten our rooms to the computers that connect us to the world, electricity is a silent partner in our modern lives. But here's a thought. Are we using this incredible power in the best way possible? Using electricity wisely is super important. It's not just about flipping a switch, it's about understanding the science behind it. Consider the vast networks that bring this power to us. It's a complex journey, and efficiency matters every step of the way. Now, you might have heard a term floating around in the world of electricity, power factor. It sounds a bit technical, I know. But trust me, it's a really big deal when it comes to how we use electrical energy. Think of it as a sort of report card for our electrical systems. It tells us how efficiently the electricity we are supplied with is being converted into useful work, like making a motor spin or a light bulb glow. A good power factor is like getting an A+ on that report card. It means we are being smart and not wasteful with our precious electrical resources. Imagine you're drinking a soda. The actual soda you drink is the useful part, right? But there's also foam on top. The foam takes up space in the glass, but you can't really drink it. Power factor is kind of like that. The useful power is the soda doing the actual work. But sometimes there's reactive power, which is like the foam. It's there, it's part of the electricity, but it doesn't do useful work. Power factor helps us understand the ratio of that useful power to the total power being drawn from the source. We want more soda and less foam. So a low power factor means that a significant portion of the electricity flowing through the wires isn't actually doing any useful work. It's like having a leaky hose. Water is flowing, but not all of it is watering your plants. This wasted energy still has to be generated by power plants and transmitted through power lines, which can lead to inefficiencies and higher costs. On the other hand, a high power factor, ideally close to 1, means we're being incredibly efficient. Almost all the electricity is doing something productive. Science! And that's what we're aiming for, making the most of our electrical power. So, if power factor is this important measure of electrical efficiency, how do we actually find out what it is for a particular circuit or device? We can't just look at the wires and guess. We need a special tool, a very clever instrument designed for this exact purpose. And believe me, in the world of electrical measurements, this tool is a real star. It helps engineers and technicians keep our electrical world running smoothly and efficiently, preventing unnecessary waste and ensuring systems perform optimally. This isn't just a simple gauge, it's a sophisticated piece of engineering. This amazing tool is called a power factor meter. Its name tells you exactly what it does. It measures the power factor of an electrical circuit. Simple, right? But its job is incredibly vital. It gives us a numerical value, usually between 0 and 1, or as a percentage that tells us how effectively electrical power is being converted into useful work output. Think of it as a speedometer for electrical efficiency. Just as a speedometer tells you how fast you're going, a power factor meter tells you how efficiently your electricity is working for you. It's a diagnostic tool that provides critical information. You can think of the power factor meter as a detective for your electrical circuits. It doesn't wear a trench coat or carry a magnifying glass, but it does investigate how efficiently electricity is being used within a system. It sniffs out the phase difference between the voltage, the electrical push, and the current, the electrical flow. This phase difference is the key to understanding power factor. When voltage and current are perfectly in sync, the power factor is high. When they are out of sync, the power factor drops. This detective helps us see that invisible relationship. Understanding how this meter works and what its readings mean is the first step towards making smart choices about our electrical systems. Whether it's in a giant factory, a bustling office building, or even in sophisticated home setups, knowing the power factor can lead to significant improvement. It helps us identify equipment that might be causing inefficiency. By monitoring and correcting power factor, we can save energy, reduce electricity bills, and even help our electrical equipment last longer. It's all about using science to make things better. Okay, so we have this cool device, the power factor meter, but why exactly should we bother measuring power factor? Is it really that big of a deal? The answer is a resounding yes. It's incredibly important, and not just for electrical engineers. Understanding and managing power factor has wide-ranging benefits. It's not just an abstract number on a dial. It's a key indicator of the health and efficiency of any electrical installation. Ignoring it can lead to a host of problems that could easily be avoided. This little number has big consequences for performance and cost. A good power factor, one that is close to unity or 100%, means your electrical system is running efficiently and is healthy. When the power factor is high, the electrical current required to produce a certain amount of real work is minimized. This means less energy is wasted in the form of heat in the wires, transformers, and other components of the electrical system. Less waste is good for the equipment, reducing wear and tear, and it's also fantastic for our planet because it means we're conserving energy resources. It's a win-win situation for everyone involved in the energy chain. For businesses and industrial operations, maintaining a good power factor can lead to significant cost savings. Many utility companies impose penalties or surcharges on customers with low power factor. This is because a low power factor means the utility has to supply more current and thus generate more power overall than is actually being used to do work. This extra current strains the generation and distribution network. By using a power factor meter to monitor and then correct a low power factor, businesses can avoid these penalties and reduce their overall electricity bills. That's smart business. So, a power factor meter acts like an early warning system. It helps us spot potential problems before they become major issues. It allows technicians to diagnose inefficiencies in electrical loads, such as motors, lighting, and other equipment. By identifying and addressing the causes of low power factor, we can ensure our electrical systems run smoothly, reliably, and economically. It truly is an unsung hero in the world of electrical management, quietly working to keep things efficient and cost-effective. It's a guardian of electrical health. Let's take a thrilling peek inside a typical power factor meter. What are the secret components that allow it to measure this important electrical property? It's not powered by tiny hamsters on wheels, I promise. It's all based on solid scientific principles of electricity and magnetism. Understanding its construction helps us appreciate how cleverly it's designed. These meters are precision instruments, and every part has a specific role to play in accurately determining the power factor. It's like looking under the hood of a high-performance car. Each component is vital. Most power factor meters, especially the traditional analog types, have some key parts that work together in harmony. Think of them as the essential organs of this electrical detector. We typically find one or more coils of wire, which are fundamental to its operation. There's also a pointer, the little needle that moves across a calibrated scale. This scale is marked with values that represent the power factor, often ranging from a leading value, through unity, to a lagging value. The movement of this pointer is what gives us the reading we need. The coils are the heart of the meter. There's usually a current coil or a pair of them, and one or more pressure coils, also known as voltage coils. The current coil is designed to sense the amount of electrical current flowing in the circuit being measured. The pressure coils are designed to sense the voltage of the circuit. The way these coils are constructed and arranged is crucial for the meter to work correctly. Their interaction is what ultimately determines the position of the pointer, giving us that all-important power factor reading. These components don't just sit there, they interact based on the electrical conditions of the circuit. They use the fascinating principles of electromagnetism, the relationship between electricity and magnetism, to function. When current flows through these coils, they generate magnetic fields. The strength and orientation of these magnetic fields change depending on the characteristics of the electrical load. It's this interplay of magnetic forces that causes the pointer to move and indicate the power factor. We'll explore these amazing coils more closely in a moment. Section 5. The current coil. Feeling the flow. Let's zoom in on one of the super important parts inside our power factor meter, the current coil. Sometimes, especially in single-phase meters, this might be a single coil, or in other designs like three-phase meters, it could be a pair of fixed coils. Whatever its specific form, the current coil has a very specific job. It's all about sensing the electrical current, the actual flow of electrons through the circuit. This coil is essentially the meter's way of feeling how much electricity is moving. It's like a sensor that measures the traffic on an electrical highway. The current coil is connected in series with the load. Now, what does in series mean? It means that all the electricity that is flowing to the device or circuit, whose power factor we want to measure, must pass directly through this current coil. Imagine it like a turnstile at a stadium. Everyone going in has to pass through it. Because it's in series, the current coil experiences the full load current. This allows it to accurately respond to changes in how much current the connected device is drawing from the supply. When electrical current flows through any wire, it creates a magnetic field around that wire. The current coil is no exception. As the load current passes through the windings of the current coil, it generates a magnetic field. The strength of this magnetic field is directly proportional to the amount of current flowing. So if more current flows, the magnetic field becomes stronger. If less current flows, the magnetic field becomes weaker. This magnetic field is dynamic and changes as the load current changes. It's a direct representation of the current. This magnetic field produced by the current coil is absolutely crucial for the meter's operation. It's one half of the magnetic conversation or interaction that takes place inside the meter to determine the power factor. Think of it as one of two dancers. Its movements, or magnetic field strength and phase, are essential for the overall dance. This field will interact with the magnetic fields produced by the pressure coils. And this interaction, as we'll see, is what ultimately moves the pointer. It tells a critical part of the power factor story by representing the current. Section 6, the pressure coils, sensing the push. Next up in our tour of the power factor meter's innards are the pressure coils. These are also very commonly known as voltage coils. Just as the current coil is responsible for sensing the electrical current, the flow, the pressure coils are responsible for sensing the electrical push, which is the voltage. Voltage is the force that makes the electric current flow in a circuit. So these coils are measuring how much pressure is behind the electricity. They are essential for understanding the other half of the electrical equation needed to determine power factor. In many common types of power factor meters, especially the electrodynamic type, there are usually two pressure coils. These coils are typically mounted together on a spindle, and this assembly is free to rotate. Unlike the current coil, which is connected in series, the pressure coils are connected across the supply lines. This means they are connected in parallel with the load, so they experience the full voltage of the electrical system. This connection allows them to accurately measure the system's voltage, which is a critical parameter for power factor calculation. Now, here's a really clever bit of science. The two pressure coils are designed with different electrical characteristics. One pressure coil is made to be highly resistive, meaning it has a lot of electrical resistance and very little inductance. The other pressure coil is made to be highly inductive, meaning it has a lot of inductance, often achieved by winding it around an iron core, and relatively less resistance. This difference is key. It causes the currents flowing through these two pressure coils to be out of phase with each other, and importantly, their phase relationship with the system voltage is distinct. Just like the current coil, when current flows through these pressure coils, driven by the system voltage, they also create magnetic fields. Because there are two pressure coils and the currents in them are out of phase due to their resistive or inductive nature, they produce two distinct magnetic fields. The orientation and strength of these fields are related to the system voltage and the specific design of each coil. These magnetic fields are the other crucial players in the magnetic interaction that takes place inside the meter, working alongside the field from the current coil. Section 7, how it works, the magic of magnetism. So we have our current coil creating a magnetic field based on the load current, and we have our pressure coils creating their own magnetic fields based on the system voltage and their specific design. How does all this magnetic activity actually tell us the power factor? It's not quite magic, but it's a brilliant application of a fundamental scientific principle. Electromagnetic induction and the interaction of magnetic fields. This is where the real genius of the power factor meter's design shines through. It's all about how these invisible forces influence each other. Let's refresh a basic concept. Way back in the 19th century, scientists like Hans Christian Ørsted and Michael Faraday discovered the incredible link between electricity and magnetism. One of the key discoveries was that when an electric current flows through a conductor like a wire, it generates a magnetic field around that conductor. The coils in our power factor meter are essentially electromagnets, magnets that are created and controlled by electricity. Their magnetism isn't permanent, it exists only when current is flowing. This is the foundation of how the meter operates. The coils inside the power factor meter, both the current coils and the pressure coils, become temporary magnets when the circuit is energized. The strength of their magnetic fields, and very importantly the timing or phase of these fields, depends directly on the current and voltage in the electrical circuit being measured. Remember, power factor is all about the phase angle, that is, the timing difference between the peaks and troughs of the voltage waveform and the current waveform. The meter is ingeniously designed to physically respond to this phase angle. The power factor of a circuit is mathematically related to the cosine of the angle between the voltage and current. A purely resistive load has voltage and current in phase, angle is 0, power factor is 1. A purely inductive or capacitive load has current lagging or leading the voltage by 90 degrees, power factor is 0. Most real-world loads are somewhere in between. The power factor meter cleverly translates this electrical phase difference into a mechanical rotation of its pointer, giving us a direct reading. It's a beautiful example of physics in action. Section 8. The pointer's dance: magnetic fields in action. Imagine the magnetic fields generated by the current coil and the two pressure coils. These aren't just static fields, they are alternating magnetic fields because we're usually dealing with alternating current AC. These fields are like invisible forces, constantly changing, pushing and pulling within the confined space of the meter. It's this dynamic interaction, this magnetic conversation, that causes the meter to give us a reading. The moving part of the meter, which includes the pointer, is caught in the middle of this magnetic interplay. It's a carefully choreographed dance of forces. The two pressure coils, as we mentioned, are often mounted on a common spindle. This spindle is carefully balanced and pivoted so that it can rotate freely or with minimal friction. The pointer, which we see on the outside of the meter, is directly attached to this spindle. So, if the spindle rotates, the pointer moves across the scale. The crucial thing is that there are no control springs in many common designs, like the electrodynamometer type for power factor, to return the pointer to a 0 position. The pointer's resting position is determined solely by the magnetic forces. The interaction between the magnetic field produced by the current coils and the magnetic fields produced by the two pressure coils creates a turning force known as a torque. This torque acts on the spindle holding the pressure coils. The clever bit is how this torque changes depending on the phase angle between the circuit's current, sensed by the current coil, and the voltage, sensed by the pressure coils. The two pressure coils are arranged, often at 90 degrees to each other, and their differing electrical properties, one resistive, one inductive, ensure that the resulting torques they experience are different. The moving system with the pointer will turn until it reaches a position where the torques produced by the interaction of these fields are balanced. This equilibrium position is directly dependent on the power factor of the circuit. For example, if the power factor is unity, current and voltage in phase, the pointer will align with the 1 mark on the scale. If the current lags or leads the voltage, the pointer will deflect to one side or the other, indicating a lagging or leading power factor. It's a delicate, precise dance of magnetic fields that results in a clear, readable measurement. Section 9. Awesome advantages. Why power factor meters rule. Using a power factor meter and paying attention to its readings brings so many fantastic advantages. It's not just some obscure instrument for electrical wizards. It's a practical tool that offers real benefits in terms of efficiency, cost savings, and system reliability. Knowing your power factor is the first step to optimizing how you use electricity. Think of it as a health checkup for your electrical system. The meter provides the diagnosis, and then you can take action for a healthier, more efficient setup. These meters truly are champions of electrical common sense. First and foremost, power factor meters help us save energy. When we identify a low power factor, it signals that a portion of the electrical energy being supplied is not doing useful work, but is instead being wasted, often as heat in the distribution system. By taking corrective measures, such as installing power factor correction capacitors, we can improve the power factor. This reduces the overall current drawn from the supply for the same amount of useful work, leading to less energy loss in wires and transformers. Less wasted energy is great for our wallets and even better for our planet. Secondly, and this is a big one for businesses and industries, power factor meters can help save a significant amount of money. As we touched upon earlier, many electricity utility providers penalize customers with low power factor by adding a surcharge to their bills. This is because low power factor puts an extra burden on the utility's generation and distribution infrastructure. By monitoring power factor with a meter and taking steps to improve it, companies can avoid these penalties and see a noticeable reduction in their electricity costs. For large consumers of electricity, these savings can be substantial over time. Furthermore, maintaining a good power factor contributes to the overall health and longevity of electrical equipment. When systems operate with a high power factor, the electrical currents are lower for a given load. Lower currents mean less thermal stress on cables, switchgear, transformers, and motors. This reduction in stress can lead to a longer operational life for the equipment and reduced maintenance requirements. It also improves voltage stability within a facility, ensuring that equipment operates under optimal conditions. So, power factor meters are truly awesome tools helping us build a smarter, more efficient, and more sustainable electrical world. Consider the science.